So last time we talked about the process, and I covered the ones called the two-stage process. Yeah, so I didn't go to the 5. So this one is more likely what we're using called the 5-stage process. So process can be just a program in execution. So it includes the program code, data execution, and the possible process stage will be new, ready, running, waiting, and terminate. Okay, so and then we have the called PCB, the process control block. So it contains the data structure used by the OS to manage the process. Okay, including the process ID, stage, program counter, PC, also the CPU register. So this is what they call the PCB. And when we try to create and manage a process, so we also call the system call, and then we will observe it. And right here, I upload a C purpose file on the D2L. So it demonstrates it's a really simple one. And then you will check we'll get the call the process ID, PID, using the fork system call to create a child process. And the child process should be able to print the message and exit. So I'll let you compile and run it. I will ask certain question. For this time, we have more understand more about the process. You should actually I should upload all of them if you're able to see it. Just you can download the C file. It's called process, and you can download it and try to compile and execute. So do you know how to compile and execute the C file? Okay, so I'll let you do it and start with the really basic one. Let me open it. So in case if you're not really using, then I will use this one. Okay. Okay. So try, yeah, process, yeah, download that one first. Yeah. For try not to look at others because I want to let yourself try as an extended question. So if you already download it and open it, then I will give you several minutes if you need to download it and open the file. Yes, yeah, that's C purpose, yeah, done. Yeah, don't open the M or yeah, that was I modified. So it's the kind of the solution and answer for your coming question. So try not to look at it. Yep. Don't look at the M, just the question. Yeah, don't open. Okay, so it's the data format you define. So we including the okay, so so when you open it, if you remember process, we want is including the process ID. So every time when we use the system call, the fork, so not only the C purpose, the system, also if you look at something that means we make a copy, create a child, duplicate from the original process to create another one. So when we every time create a new one, say clone a new one, so we have a new process ID. Okay. So in this program, if we execute, so what you see, try to compile and execute. So what's the result?
We've got errors on.
You should see. Process. Input statement. Let me see. Suppose I'm expecting you should able to get like two child process with two different.
Yeah, let's just say that whatever that library. Okay. Sometimes set up that in mind. Let me see how many. No, none of you. None of you. Okay, let me tell you the first thing. Because I think because I'm a PK, I already prepare for the C purpose. So that's why I already install all the extension on my. So let's see the VS Code. It's the header file, yeah. So included. That one should be belongs to the this one. It's called we using the weight to call it. If we don't use it, then we cannot use the .h. Let me see. If anyone can figure out, then we can say wait. Okay. So right here we'll execute download the process without the M. Okay, let's see. Say that it's open. Not
No, on Windows. Windows. How about any Mac user? They want. Okay. And if you don't have it, so try. Let me see. Then I need to change the syntax. No, we Okay, we can try to yes. Let me change it. Because we need to wait for the process. So no, then maybe let me check like on Windows what kind of code can we apply to wait? Okay, implement subsystem. Okay. So this one is not a good solution. We need to include other library. Try not to let you. Okay. Okay. If no, wait, let me see. Maybe some people, they will provide the weight data file. Okay. Anybody can find the GitHub link right here. So try to, let's see if I can, somebody already implement, upload the weight header file. Let me download it and then upload it to the Git. So if you need to use it, save it. So just put it together with your file download. So you will check. Okay. And try to, if you're using a Windows system, try to download the weight header file, and then let's see if you can import the H file weight. So because you're not using really the system weight file, so just import using your own path. Yeah, put it together. Yep. And let me check there. If you need to. So if you need to, here's an example for the C purpose. Just include with your own header file, so you can put it together, too, and then you can include it. Do you have a? Okay, so we create. I upload the one is the weight file, so it's until either you can include that one. Yeah, like you do. The weight file. Try to do it this way. Connect to your front. Okay, then maybe I will save a Docker image. So set up your front. So I think it's easier to when make it for later for the lab. So I will create using Docker and create your front image. So you can run it on your input system. So I will have to present all the requirements. Okay. Right now you may try to connect to your EC2 server if you have it, and then just under your folder, because your Windows is supposed to have a GPFS, so you can extend and when they could include all the okay, you can try to do. So try to letting you to if you cannot do that, then I cannot move forward. You just listen to me. So Hold on. Can you do that or no? Okay, so it's still not, it's flowing, so I was in the reverse system. It's pretty, but as a fix, I will do that. Yeah, if when I'll share the EC2 server to you, so you can connect to it and try to execute. And yeah. And then later I will create a Docker image with the Ubuntu, so we can run all those C pipes. We'll share this part to you. Go to the, okay, let's say please check the announcement, and because once you download it, you need to change the property. Try to access it. So you connect to the server. So if you connect to the server, so you can under your like home directory, so you can use sudo nano and then create the process.cpp with the place successful and control second control X and using GCC run. So are you fixing? Also is set, also in the system and that. So we don't have when I submitting you to connect to the server, so this is the Linux system. So that's it.
The announcement for the Windows, you need to take a photo, so you take it. And announcement, so I shared the session. And download the certificate. For the certificate, you need to choose the topic.
Well, apparently they don't have GCC installed.
Okay, so you also need to install GCC. Okay, if it's not working this time, then okay, I will prepare a Docker image. So I will tell you in the next time the lab, so we can use the Docker, get the image. You can git code and prepare the GCC. Yeah, yes. Actually, yes, we need to install the GCC on Ubuntu. Follow the steps, but I will prepare the image to you so you can follow it. And this time, then just I will stop right here for the
I just tell you how this one's showing, and then you can try it at home later or on the lab. So if you remember the process, we talk about the process, and then when we wait. So right here we have the one if the in the beginning when we execute the file. So everything right here, the program we're writing is simulating how the OS manage or like how the program create. So we try to give the some information data about the our process. So in the beginning when we fork the execute, the PID should be empty, so it will be less than 0. And if we equals to 0, then we will call the function right here. So we will print a message and then get the PID. So this one is the pre-implement function for the like C purpose library. So when we call this function, it will get the ID of the process, and then it will exit if no. If else, like if it's not equals to 0, then we will run a program called the wait. Change it. Okay. So and then we will wait for it and then until the child process finish. Once you finish, and then we'll go back to the primary the parent process. So right here, if I compile and execute, so it will run the child process first. It comes with the PID state 25 to 89. So this one is the child. So and then we will execute the parent. So it's like we try to get into the first, it's like create, and then when we call the system call, then we will generate a system called the child process. And because right here, because in the stack, if we remember the stack, so the child, the next one will execute first. So that's why the child comes first. And with its the ID. So after it finish, so after finish the child process, so we already remove, because in the stack we always say last in first out or like first in last out. So it's like this. So the child process we print out the ID. Oops, sorry, and we will execute the rest will be the parents process will be right here. So you can see the sequence will be like this. So here is always the 101 that's showing using C purpose, showing the process with the ID using the system call. Okay. And when you look at it, then we will say, okay, so what's really actually happened when we use the system call? And how can we second say, okay, how can we verify that the process creation was like successfully? And also what the process ID of the parent and child process. So whenever you see it's like it's a 5-digit number and then just +1. So based on this one, you see, okay. So when it really like execute, so we will create a new process, just like duplicate and calling it. And then a new one is referred as like we call it the child, or say parent and child. And then the original is called a parent. So both of them, they continue execute from the point where the fork was they call, but they are different process ID. So when we do the multitasking, actually for the extension for the task, is like we need to simulate how to doing that tasking, because right now we have 2 trial because you cannot do it. So I will just like wait for next time. I'm just like ask you to do that. And all of them, they have their own ID. Even we call a function like under, but when we have a fork function, and they are all treated as a different process. Even we look at this program, we say, okay, it's just same, but when we call another program to duplicate a child process, then will be 2. Yeah, so they are identical. So they are not the same, but they have a same exactly same source code, like what they're executing. Then we just like go back to the question. If you remember, last time we think about the like how about using the resources allocating if I have two program. So here is a good example. If I have exactly same source, same process, child and parent, I need to execute. So I request the same resources, right? So they are like, if under the multitasking, maybe I assign to different CPU or like different thread to handle it. If request, then that means our OS need to design. Okay, so if I execute this one, does it if I have a thread to allow it to do it? So if like look at this really basic condition, only like two process, but with sharing one resource, assuming that in this way, then okay, just one thread, allow or not. Or in the advanced question, if you remember the use case, I have like multiple ABC 1 or 2, then I need to minus it. Then we need to enter mechanism like to always like prevent the deadlock, also called the safe mode. So in the example I gave last time, right here, for the question 2. Okay. So for the question 2, we say like try to ensure it's no deadlock. So they already have a kind of like sample code how to prevent the deadlock, or like another one is to make sure the safe mode. So that's how we handle when we have multiple processes. Okay, we are working together. Let me go back to okay. Yeah. And then next question is about how can we verify this process creation was successfully? So we can verify it so by just checking the output of the program, so which should include the message for both parent and child person. So if you look at here, the output message, if you're like completely executed, and then you will get the PID, and then it will be it will call the exit function and return. So it's done. So for a child, so the PID is equals to 0. Okay, it will call the child. If no, then it's parent. Okay. Well, in the beginning, like the PID is nothing, so that's why. And then right here. Also, we can using the PS. PS is the command to check the process appears in the process list. So right now I have one is executing right here. It's called I have the PID is 24896 TTY 003. So this one is in the command, and I can use the terminal right here. So this one is same. You will check like no matter. So right now I open one more, so I have get another process with different ID. Okay, so for this one, I think everyone you can check it using your PowerShell. What does it come up if you using PS to check the process status? If let's say I open 2, you will see I have a 2 PID. Can you see it? So you can use the command, it's called PS. Execute on your PowerShell or terminal. So when you check it. So anybody try to use the PS to check the process status? So what does it, you know? So you see, you have two terminal and okay. Okay. How about others?
Yeah.
Okay, so what else? You, I think you have more than that, right?
Yeah, I got it.
Yeah, Windows. Okay, so you see right now, in the OS, you have plenty of the process is running under this system, and then we have different. Yes, yeah. So then you add it. So some of you ask a question: why the PC that is not always not stable, you know? So even you kind of doing nothing, kind of waiting, and you see you have so many processes. So bunch a lot. Yeah, so even if like I just say open a VS Code, open a browser, you have this system, so it's like actually lots of process is running in time. Okay. So all those successful processes they're executing, or the operating system manage them. So you will see over there. So you will see the system. So when we look at it, so what are the process ID of the parent and child process? So we see a process ID of the child is returned to the parent process, and is printed by the child's like printf statement, and then the PID of parent process is printed by the parent statement. So when you see the print function right here, actually for two different processes, the child and the parent, they are executing their own printf, the printing function. And why we're doing this, we add the wait. The wait is that we let the child process to finish, then we will do the printing. If we don't wait, then we execute the parent first, and then let the child to execute. So I will see. Okay, this time I execute one more time, and then the parent will be changed to 61, and then the child process will be 65. So it will see it change. Because we take more time, and then we have more stack. And let me see. Using PS, what else comes up? Still same. It's a map, so it's just showing the one we're executing right now. Okay. So here's the example. We're checking the PID, and because we also, well, we cannot. For the second one, here's the step. So you can use the PS, AOX at top, or the X top to check all those the process. So you can use it to check it. But I don't think I have it. So right here. Top is other process. So Windows Server assume is running under the 4533 right here, and then items is the terminal I'm using right now, and then the Google Chrome. So they are even from there they have different. So they keep like moving, complete, finish. They keep switching. So you see it's moving right now. Okay. So how about all yours? So you build this one for Windows, keep refreshing, but I don't know the Windows, does it comes out any of it working to use?
The Windows doesn't have top.
Oh, okay.
I think.
So sorry for the Windows user.
But I think it's.
Let me check. Okay, if somebody found the comments, like how can we use let me see Windows check process. Task manager explore or like beta purpose. We don't have a command. Okay. So sorry about it.
The very bottom, the packages, and then
Okay, so you can, it works. Okay, good. Good job. Good. Okay.
And then we have to get it. Okay. Yeah. Sorry for Windows user.
Okay. Here's like some of the tools we can use to check the process we are executing for the system, and when you look at it, like it's always keep refreshing because even in this moment I don't touch anything. So in the background, there's lots of service they're executing, and even you see because I'm using Zoom, so Zoom always like occupy on the top, and then it takes almost with Zoom like 30 something. And then my Windows server also, they are just like competing for the top tools. Okay. So what's your top 1 or 2 service? No service, the process occupying your CPU.
in the PS or the top one.
Okay, because you are using VS.
You're
Okay.
using the PS one, it's some package.
Okay. Okay. The framework, so they are the background service they're using, so not yours. Okay. Okay, good. So based on this, like if like how does this, like if we look at this, how the system schedule or like switch between multiple processes, and also how does the time consuming tasks affect the process execution and scheduling, and what kind of observation can you make about the process multitasking? So based on this, okay. So how do the process change during the execution? So initially all the child process, like if we know what's like they're all in ready stage. So when we start to execute, so we start to like run, and when we call the sleep, then they will wait. Okay, so it's the 5 stage. So we're going to cover here, and then until sleep duration is over, then once they complete the execution, they move to terminate. So we stop. So here we'll go back to our lecture. If you remember, we have the 5 stage. Okay. Before we talk about the 2-stage process, just like not running. Okay, really simple. So this process not ready is not running, and then we dispatch, then just like running. If we finish, exit. If no, or like we say pause or sleep with different terms. So we just say put it back to not running. So when we bring the process back to execution, then go back to running stage. And when we right now what we talk about nowadays, there's actually we have more than only 2. It's not enough. So that one's called the 5-stage process. So when we create a process, it's called new, and once we admit it, so it changes to ready. So ready, dispatch, or like we execute, so we go to running. So once it finish release, it will go to exit, or is timeout. Because we have, if we look at the process we are executing right now, actually we have so many. And because the instruction they're taking terms, so actually we have some different mechanism like round robin. So like maybe within the time limit. So I will do this process. So if I cannot finish it, I will put it back to like ready, just like let it wait, and then wait until taking terms and come back to this process that I will put it to running and execute again. Okay, if still not yet, put it back. If it's complete, it's go to the exit stage. So I release it. So if there's some event happen, sometimes we say interrupt, right? So we do have an interrupt, then we just like wait. So plug it and put it back to ready, and then wait for next time and execute it again. So we call it the 5-stage process model. So it's the nowadays like the process they're doing right now. Okay. So let's say if we have the like process A, they have a running time, and then here will be like ready stage waiting, process B waiting, and then we will put it to running. And if some interrupt comes out, and then we just put it to block, and process C just waiting, ready. And then when you put it execute, and we're running, and maybe it's not yet finished. That means we always have timeout. Then just wait for it. And wait for it and until the next time. Then we will bring it from ready to running stage. That's how the 5 stage working. And let's say if we have using like 2 queues. So one is called a ready queue. So we put a it's more like fair, like first in, first out. So I have one process comes in. So I will put it in the ready queue and then put it dispatch and then bring it to the processor. It's finished. Release it. If no, time I'll bring it back. So put it back to the queue. And if I have some like interrupt comes out, event pops out, so I will put it to block queue and then wait and then until the event finish, compare, and they'll put it back to the ready queue again. So they're waiting in the line. It's right here, and then we can increase more. So here will be like multiple block queue. So maybe we have more than one event happen. So we can like, okay, this one for event. So wait here, event 2, event N. So we can, it's possible have a multiple. So it's not say only one. So we also using queue to handle it first in, first out. Okay. Then we say, okay, then how about the suspended process? We are swapping, so it was moving a part of a process from the main memory to a disk. So we are transferring, or like when none of the process in the main memory is in the ready stage, and then also spread one of the block process out to the disk and to a suspend queue. So this is how it works. So right now we will add one more stage right here called the suspend. So new, ready, you already know, running, exit, and then block. Okay. So when we have a block, and then we put it to suspend queue. Or like for others event occur, then also like just back it. And after suspend, sometimes we will activate, then we'll always bring it back to the ready queue. So right now we have like so many different queue, like block queue, suspend queue, also based on the queue time, and then we put it back to the ready queue. And getting more complicated. So if we get one more block queue, so you will see right here, maybe running. Here's will be like we have the new. So just like you see new, ready, running, exit, block. So if we only have one block right here, but if we add one more, so we'll be like one more suspend or like ready, suspend, and then we will send it, okay, from the, just like ready queue for ready queue, like this, like ready queue, send it to ready queue, activate, and then from the ready queue, bring it to one. So we have two suspend status, okay. So, you know, it looks so complicated. So the process is not like immediately available for execution, and the process may or may not be waiting on an event. So they're all possible. So the process was like placed in a suspended state by an agent, either itself or parent process or the OS for the purpose that prevent its execution. The process may not be removed from the stage until the agent explicitly order the removal. So it looks like why we need a suspend. It's like if you learn that like parent, if we look at the example code, the first one, parent ID, child. So when we execute, we have multiple functions, maybe like different functions. One is relied on another one, maybe the asynchronous. So maybe I try to execute a certain statement, and then I need to get the data from the server API. But within that time, then maybe I shouldn't execute this part, like this statement, because I need to waiting for, because for the network, we need to connect to the server, API server, get the return of the JSON file and waiting for it. So without the reply of the JSON file, we shouldn't execute this process or like the function of that part. So we just put it like to the plot it and put it to suspend. And if we using the once they suspend, just right here. So we plot it and put it to suspend and wait until maybe, okay, so the event comes out. Okay, I got the return, the JSON file. So I will put it to ready queue. I'm ready to execute it again. So it's how it works. Okay. And also, one of the reasons we talk about the scrapping, so they always need to release a sufficient main memory to bring in and a process that's ready to execute. Okay, so here's the reason, and the other OS reason may suspend a background or utility process or process that is suspend, causing a problem. So it may because the OS is always predicting, they always calculating if it's available or okay to execute, if the next stage is safe to execute. So we need to know, okay, is there enough resources or is any conflict for like let those process like execute? If there's a possible, then I don't let this one to execute. So this one. So interactive user request. So the user may wish to suspend the execution of a program for purpose of debugging in connection with the use of resources. So sometimes we will break, sometimes we will pause it. So or wait. So we have some like function in program to like let it keep it. So wait. So we put it to wait. Maybe if we wait for right here, you will see I just wait. I didn't put it, so it's just the default by time. Or sometimes you are waiting for maybe 1 second, 10 minutes. You never know, but just like for certain purpose, depends on your program. Or like for some background service, you need to check the there's some service will keep them checking alive of the hardware or devices, or like we call it a heartbeat. So heartbeat is like, it's like the impulse of your, okay, it's make sure it's alive. So for the IoT, slightly far away topic, but it's like kind of like this. So for the IoT stuff, we have a process. Most of the time, it's just like have a service. We will take it like, I want to check it frequently, make sure it's always working, maybe every second. Actually, what every second is pretty slow. Like we wait really long time because in computer it's waiting like nanosecond. And maybe if that service is like execute like once per day, then you can just like wait. So we can put it like really suspend until like 24 hours, or like you check the time based on the time clock, and you can execute like at like midnight, something like this. And timing, we say like maybe execute this way here. So it's getting more like periodically. So maybe an account or system monitoring the process, or maybe suspended while waiting for the next time interval. That's how we did like those like habit. And parent process request. That's already the parent process may wish to suspend execution of the decent to examine or modify suspend process, or to coordinate the activities. So it's kind of like this. So it's all of that possible reason. So it just suspend, just wait over there. Okay. So right here, let's see. So, okay. And in the exercise I mentioned, we have the called the control block, the PCB. Okay, so right now, including the process ID, the stage, program counter, CPU. So right now we will move on to know more about what is PCB and what's the data structure. So for if we have a multiple process like P1 to Pn, in the VM, if you still remember the virtual memory. So in between we have some mapping in compared to the computer resources. If you still remember that we have the kernel. Kernel is the kind of like we say the interface between the hardware and the application. So for when we writing a program or like for those applications, we don't really need to consider, okay, how can I really communicate with the CPU or the RAM or the hard disk computer data. So because the kernel, they are the interface, or you can say it's the driver to help us to handle all these like requests or action. So sometimes we will access to the main memory directly, or sometimes we need to connect to the IO or just the same to the processor because we need to connect the ALU math calculation. So in our OS like control table, like including the memory files, so include the process. So in the process, we have the called the primary process table. So it's a all the process we are going to execute. And inside within the process, we see the process image. So with the details and then memory, there's a memory table, IO, we have IO table, file table. So all of them, they have their own. Okay. And about the memory table, so used to keep track of both a main with a real memory or the second memory, sometimes like virtual memory. So we say the virtual memory, if you remember, if you learn the computer architecture, so do you know what's, well, I would say, but as we say, did you heard the term second memory? Or like they say, what's second memory? So what's second?
It's where you use the external storage, something like, right?
External, that means your hard drive. Yes, your hard drive. Yeah. So sometimes we say it like main and secondary. And if you remember this one time, say, okay, we use our hard drive to create our VM because just imagine it, because the main memory is your table. It's right here. So your table size will limit it like how many process like you can put it on it. Okay, so if your table like this, you can put the laptop, like everything over there. So of course, when you have a larger table, then you can put more stuff. So you can like access easily. Just imagine maybe there's a locker right here. So it's your second memory. So it's your hard disk and you need to access it. Then you need to go to grab it and then bring it to here. And sometimes it's like you don't have enough main memory. Or like if we remember suspend, sometimes we need to wait. Well, we need to free up the memory, and we need to put the process to suspend. Actually, it's taking to the second memory, or we create a VM to kind of like extend your desktop. So because the desktop, you can have a number sequence, right? 0 to, let's say 100. But 100 is your maximum for your desk size. But I still need to put more process on it. Then what should I do? Okay, I say I use the first two, the maybe first row of the locker right here, and then I say okay, that one is a VM. So I say 101, then you will know. Okay, I will go to the or like I will using, actually we have an offset. So I will say okay, go to 1, and I will add the offset. Then I know I need to access to the secondary or the hard drive. That's what we say the virtual secondary memory or VM. So process maintained on the secondary memory use some sort of virtual memory or simple swapping mechanism. Also, we do have some mechanism like, okay, take it out, bring it out. Yeah. Luckily, because we changed to SSD, so the so far the whole the VM or like swapping speed like really increase a lot. Included in the main memory table. So we will like allocation of the main memory to process, allocation of the secondary memories, virtual and scrap, and then protection attributes. For example, share memory region, read-only region, and the virtual memory address translation map is really top because we need to have a translation for the VM because it kind of like isolated part. So also, we can declare the size of the VM size. Sometimes we can do it by ourselves, like by system. preset, or like the OS help us to like dynamic, do it dynamic. Yeah, so really depends. And about the IO tables, so it's used by the OS to manage the IO devices and the channels of the computer system. At any given time, an IO device may be available or assigned to a particular process. Yeah. And why not? Because we have multi-thread and then we can access any. And also the driver, because all those IO also have an interface, so like they communicate with them. And for a file table, information about existing files, their location, current status, is it open, read, or write, etc. And the information may be maintained and used by a file management system, in which the case like OS has little or no knowledge of the file. So the OS really don't have to need to know it. In other operating system, much of the details of file management is managed by the OS itself. So it depends on. Okay. Why now we move on to the process tables? Okay. Okay. So it must like be maintained to manage a process. So this one's important. And there must be some reference to memory, IO, and files directly or indirectly. That's how the process table doing, and the tables themselves must be accessible by the OS, and therefore they are subject to the memory management. So there are definition used, and later we will try to give you some. And you will see like all the table list, then we have the process image. So we dive deeper in. So inside the image, the process image, we have the user data. The data like this one really the user, but the one is like the program itself for execution. So the user program, so the program code going to execute, and stack. So last in first out stack, used to store the parameters or call return address for the function system call execution. So we'll know, okay, so we're going. Also, we have a heap, and heap is a dynamically allocated location to hold the modifiable data. So that one's the heap. Okay, so if we have some like data variables we need to modify, so we put in the heap. Okay, and PCB control process control block. So the data need by the OS to control the process. So all here will be stored in the image, process image. And the process attributes will be including like the identification, state information, and the control information. So that's what we're checking in the attributes. And here's all the details right here. So identifiers. So, and then the user visible registers. So we for the process identifier, we including the user. That means the program itself. Also the identifier process that like create of this process. That means the parent process, because we have parent child, if you remember, we call the function. And then we have the stage information. So those stage will be like called the user visible register. It's like one using refer to the machine language that the processor execute while in the user mode. Typically, they will form like 8 to 32 of this register. Although some like the RSC implements have over 100. So we save it in the register to see, okay, what's the status of it, and then control and states register. So when we talk about the PC, the program counter increasing, and then some condition code, and then we solve most of recent the arithmetic or like logical operation. So we're adding or the status information. So over here, and also the stack pointer. So increasing. So we will know that each processor have more or like last in first out system stack associated with it. So a stack is used to store the parameter, calling address for procedures and system call. So here's the stack. So all the program itself, because we have different functions and we are going to call. So we save right here. So inside the stack pointer. And we have the control information about the scheduling state information that we type. And so the information included right here. So we'll be performing the scheduling function. We are not yet covered the scheduling. So just look at it. And then when we really cover the scheduling, then you will know better about, okay, so when we have different processes, so based on the state, so we know part of it is that, okay, we have the new, confirm new will be ready running. If it's finished, we'll exit. If no, we will go back. Yeah, so we will maybe they call block or well, we have a suspend or like what. But basically it will be 5. We sometimes we like make it simple, just 5, then we don't talk about suspend. And also we will have a different priority. For scheduling, we have different priority. Sometimes we assign it like by the program itself. If we have the child, the parent child, we'll assign, or the OS will change it. So this one will affect which process will be handled first of all, like maybe in our mechanism, how to swapping the process in the queue. The first one we're using the stack queue, stack to save the calling, and then using the queue to handle the other process, right? But actually taking times. But sometimes if we have a high priority, then what should we do? Or like something is more important, we need to do it first. Then we should have a mechanism to handle it. So we need to add the priority. And then scheduling related information. So just depends on the scheduling algorithm use. So the example of the amount of time the process has been waiting and the amount of time the process executed the last time it was running. So actually, if you hear these two parts, we're going to cover later about scheduling, is if this process is waiting too long, then should we let it execute first? Or like maybe there's a mechanism is I say, okay, if this program is small enough, then I will try to finish it first. So there to right here already is a hint to different scheduling. First, okay. And then we have the data structure, but this one we will cover for the rest. And right here, we'll just cover the identification first. Okay, each process will assign a unique numeric identifier, and then there must be a mapping that allow the OS locate the appropriate table based on the process identifier. So either it's self-identifier number, or we should have a mapping table to match it. Okay. And many of tables are controlled by the OS may use the process identifiers to cross-reference process table. So if you remember the process table contain all the like process image. And memory table may be organized by the provide a map of main memory of identification which process assigned to each region. So we know, okay, which process they're located in which part of it. So it's similar to the IO or file table. So when the process communicate with one another, the process identifier inform the OS of the destination of a particular communication. So we'll know, okay, which address should be accessed to. And then when the process are allowed to create other process, identifier indicate the parent and descendant of each process, just like have a relation, the PID controlling. And for the state information right here is a consists of content of processor register. So when I talk about the, and when the process is in running stage, of course, it's current information in the register. So running. So when the process content like switch out, then we must save this information to memory to freeze the current state of the process. So actually in the execution, so it always happens when we load the app process. So it's right here ready, and then we always like scrapping, like move into next stage, and move out, and next one comes in. So that's how the OS do it. And if we are just a single tasking, so I only handle one. But in reality, the computers they have multiple core. We are doing like multi-thread. So actually, we need to swap all the process. Then that's important. We need to trace like, because when we are scrapping, moving, so the memory may change, or like when we change it from the main memory to secondary go back, or if we don't have enough memory, we have a VM, and we need to set the offset. So they all like have a table to trace, okay, or indicate, okay, where this process, or if for the parent process need to get a wait for the child process, then what should I go to access? Then all this will be like safe in the information. And I think almost is the time, then I will not talk about the register. We'll cover next time. And I will prepare the create the using Docker. I will prepare a tutorial for next time, or if I will post it like kind of like in the weekend. So if you want, then you can download the Docker, install. If no, you can. If you have some problem, you can wait for me. So I will go through in the lab. So tell you how to install it, so you can execute and then have some C++ program. Otherwise, I think you all have a problem to like work on the assignment later. So that means you maybe have an issue to run the first assignment, right? Like that was okay. Okay. Okay, good. Yeah. So just like for safety, also because I think I also want to introduce Docker and sometimes for the environment, so I try to add it. Okay, and that's it for today. Thank you.